Hi, everybody. Welcome to the second ACME Materials Research Seminar. Today we have Dr. Yafei with us. He is just beginning his postdoctoral assignment at the University of Washington. He got his PhD from UTSC and then completed a quite successful postdoctoral position at the University of Texas, Austin. So Yafei's been quite prolific looking at his record in terms of publications and research. So I will have him share his screen, but he's going to be talking to us today about his, I think his research at UT Austin, and we'll go from there.
Hey, thank you, Adam. Thank you for introduction. And I also want to thank James for his invitation to give me this opportunity to present our recent works. So today I'm going to talk about the variance of quantum Hall effect, which mainly includes three parts. First is a 3D quantum Hall effect, which is a collaboration with experiments. And second part is about orbital train insulator. And finally, it's a high order topological insulator. Yeah, here's the outline, mostly about the three parts. Yeah, let's start from the quantum Hall effect. So you see that it's well known that in a two-dimensional electron case, if you apply a vertical electric field, vertical magnetic field, the 2D electron gas will form a lambda levels. So this is discrete lambda levels in a 2D system. When the chemical potential lies in a gap between two lambda levels, you can find a quantized Hall resistivity. And meanwhile, the longitudinal resistivity goes to 0. So these are two hallmarks of the quantum Hall effect. So for the quantization, an energy gap is very important because there's an energy gap, the longitudinal conductance is 0. However, the transverse one can be non-zero, and it's quantized. So we can generalize the two-dimensional quantum Hall effect to a quasi-2D. It means you can have a lot of layers of two-dimensional electron gas. If there is no interlayer coupling, each layer can be regarded as a 2D system. So under a magnetic field, each layer will contribute to a quantum Hall effect. You see the electron move along the edge of each layer. And when there is a little or a weak interlayer coupling, the discrete lambda levels can have a finite bandwidth. So this bandwidth is proportional to the interlayer hopping. When the bandwidth is much smaller, the Fermi surface of this quasi two-dimensional system will become will looks like this. It has a small bump here, but it's not closed along the z direction. So you see, for a two-dimension, for the kx and ky plane, the Fermi surface is a circle. However, when you go along z direction, it will go from one brilliant zone to another. There will be no closed loop, closed Fermi surface. So in this case, when the bandwidth is much smaller, is much smaller than the cyclotron frequency or the energy gap between the different lambda levels, you can regard this system as a stacking of two-dimensional electron gas system. So the physics is quite similar to the two-dimensional case. So there are several experimental realizations of the quasi-2D quantum Hall effect. For example, in the gallium arsenide aluminum or gallium arsenide superlattice. In the superlattice, the two-dimensional electron gas is at the interface. So if the interfaces are far away from each other, their hopping can be very small, interlayer hopping. So in a reasonable magnetic field, the cyclotron frequency can be larger than the interlayer hopping. So you can find the quantum Hall effect. So, but yeah, you see here the Hall resistance is much smaller than the quantized Hall resistance for a two-dimensional system. So it's contributed from like 50 layers. You can also find this quasi-2D quantum Hall effect in this compound material. It's a layered material, and the interlayer tunneling energy is also very small. It's about 1 MeV. So in a slightly larger magnetic field, you can also find a quantum Hall effect where the Hall resistance seems quantized and the longitudinal resistance is close to 0. When you go to a realistic three-dimensional electron case, the bandwidth along z direction is usually in the order of eV. So if you want a quasi-2D quantum Hall effect, if you want a cyclotron frequency larger than the bandwidth, you will require a magnetic field of tens of thousands of Tesla. So it's a very large magnetic field and cannot be realized. However, there is another way to realize the three-dimensional quantum Hall effect, which was proposed by Halperin many years ago. So for a three-dimensional electron gas under a magnetic field, the implant motion of this electron will be as similar, will form lambda levels, but along the direction it's dispersive. You thus will have a Fermi surface here. And this Fermi surface is actually a quasi-1D. It's actually just along the kz direction. You have a Fermi surface. Therefore, in this 1D system, in the presence of interaction, for example, electron-electron or electron-phonon interaction, you can open the band gap between these 2 points. There's some instability here. So once the interaction drive a band gap here at the Fermi energy, the system then become an insulator. So this band gap can therefore protect these topological phases, make the Hall resistance quantized, and the longitudinal resistance goes to 0. So this is a theoretical proposal at that time. And recently in our collaboration with experiments, we find in zirconium telluride material, this mechanism can be realized. So this part is mainly a experiment work. So the zirconium telluride, you see zirconium, and it's a transition metal. And the telluride is a heavy element with strong spin orbital coupling. Here it's a lattice structure. It's a quasi one-dimensional lattice. So you see along this A-axis, the atoms form a one-dimensional chain. And along Z direction, this one-dimensional chain form a two-dimensional plane. And this two-dimensional plane will stack along the B direction and form this bulk material. So in this STM work, you can see clearly this quasi-one-dimensional structure of the material. This material has been studied in last century because of its anomalous resistance dependence on the temperature. So you can see as the temperature increases, the material first show the resistance of the system first increase and then show a peak and then decrease. And another point for this material is thermoelectric effect. This thermoelectrical effect is usually large in materials with strong spin-orbit coupling. And recently, this material has attracted much attention because of its topological property. Based on this calculation, this zirconium telluride is very close to the phase transition point between a weak topological insulator and a strong topological insulator. And some experiments also claim it's a semi-metal. So it's not a, it's still under debating now. So for the zirconium telluride, the electron gas is first is a three-dimensional electron gas. The first characterize this electronic property of the system by using the Shubernikov-Hasse oscillation. So by applying a magnetic field B, this the lambda level will form perpendicular to this B direction, and when you change the magnetic field, this the density of states as the chemical potential will change. So when this cyclotron orbital is forms along this Fermi surface, there will be a peak at the density of states due to the formation of lambda level, and when it's not, there will be a dip. So the density of states at the chemical potential will change as the magnetic field change. This will influence the resistivity and make it oscillate. So by study this periodicity as a function of 1 over B, one can extract the area, the cross section of this Fermi surface. So this SE is the cross section of the Fermi surface along different directions depending on the B field. So you see, by applying B field along X and Y and Z directions, we can also always see the oscillation. So it means the system is actually, the electronic system is actually a three-dimensional electron gas. Because, for example, if you have an open Fermi surface, when the B field is lying X or Y direction, there will be no closed loop on the Fermi surface. So there will be no oscillation here. So after characterize this electronic system, they measured the Hall resistance and as a function of magnetic field B. So yeah, this red line is the longitudinal resistance, and this blue line is the Hall resistance for this system. So now you can see the hallmarks of the quantum Hall effect. The first is at this B field equals about 2 Tesla, there is a nearly quantized Hall resistance. And meanwhile, the longitudinal one is close to 0. But now you see, in the measurement, the resistance is very small. The system have a thickness of about 0.1 centimeter, and the mobility of the electron is it's very high. So the highest record for graphene is about 200,000. So, for this zirconium telluride, the mobility is close. So these two hallmarks suggest that the system exhibits a three-dimensional quantum Hall effect. So, yeah, but it's still not very clear whether this quantum Hall effect is induced by the charge density wave. So in order to characterize this, we studied we compared the experiments with the previous Schultz theory. So first, we can extract the thickness of this system, the thickness contributing to the quantized Hall resistance. So yeah, in this calculation, you see this lambda Q represents the thickness of the material, which contributes a quantized Hall resistance, which is about 5.8 nanometer. And this value is very close to the Fermi surface instability induced periodicity. So if there is a Fermi surface instability, there will be a band gap open here, and the electronic density will have a new periodicity, which is equals to 2 pi over Gz. This Gz equals to the 2 times of the Fermi wave vector 2kF. So by using the Fermi surface obtained here, we can estimate this new periodicity based on this Fermi wave vector. So it's about 5.6 nanometer. This value is very close to the thickness contributing to a quantized Hall resistance. Therefore, the result suggests there is a Fermi surface instability here. So we show that for different samples, we have 4 different samples show the similar behavior of the three-dimensional quantum Hall effect. We measured the lambda Q and this lambda F for different samples. You can see they agree with each other very well. So this result suggests there is a Fermi surface instability here. This is the Fermi surface instability was later suggested to be induced by electron-phonon coupling in following up theoretical work, which is done by Fang Qin and Xin Chengxie Hydro group. So, but I'm not going to describe the details in this theoretical work. Yeah, but the basic physical picture is that the quantum Hall effect can be generalized to a quasi 2D and 3D. For the quasi 2D system, it's basically a stacking of 2-dimensional quantum Hall effect. And for a 3-dimensional system, you can have a closed Fermi surface, and the Fermi surface instability can drive a charge density wave and form quantized Hall conductance and 0 longitudinal resistance. So this is called a 3-dimensional quantum Hall effect. Yeah. So if there's any question during the talk, please feel free to ask, and don't need to wait to the end. So that is basically the first part. And In the following, I'm going to talk about some theoretical works of ours. So it's about the translate. The second part is about translate. And our focus is on the orbital magnetic moment in this translate. So the first train insulator is proposed by Haodan in 1988. The key idea of this proposal is try to find a quantum Hall effect without a magnetic field. So in this proposal, the author studied a honeycomb lattice, and he showed that if there is alternative magnetic flux for A and B, the magnetic flux are opposite. So the total system have a zero magnetic flux. However, when you're considering a hopping loop, for example, this loop, there is a net magnetic flux, which is same as A. So this magnetic flux will introduce will be attached to the hopping of this system. So without this magnetic flux, the system is a semi-metal with a direct point, and the presence of the magnetic flux will open a band gap. So this make the system become an insulator, and the system have a this red line shows the distribution of the Baire curvature. This Baire curvature is actually a anomalous velocity. So in the presence of the electric field, the momentum of the electron will change. So the change of the momentum will fill this Baire curvature as an effective B field in momentum space. So this effective B field will contribute to a transverse velocity perpendicular to the electric field. So if this Baire curvature is now zero by integrating over the brilliant zone, which means to integrate over all the electrons, if it is not zero and give rise to a quantized train number, this quantized train number will give rise to a quantized Hall resistance. So yeah. So in this theoretical work, the author says this particular model is unlikely to be directly physically realizable. However, less than 30 years, this model has been realized in an ultra-cold system, ultra-cold atom system. So it means this is quite inspiring. For physics, for theoretical physicists, you don't need to worry about whether your model is realistic or not. You just study some new physics, it's okay. Yeah. Although in this system, the net magnetic flux is zero, there is a hidden orbital magnetization order. So before we show the results, let's first take a look at the modern theory of orbital magnetization. People didn't realize that there is orbital magnetization in this Haodan model. It's simply because at this year, the theory of orbital magnetization have not been developed yet. The modern theory has been developed about 2005. So the orbital magnetization have two contributions. First is from the bulk contribution. So you can see by assuming that the Bloch bands are occupied by the web packets. So the web packet can have a spin up, can have a spin. This spin can have spin up or spin down. This will contribute to spin orbital, to spin magnetization. However, the self-rotation of the web packet can contribute to an orbital magnetic moment for each Y packet. So it will contribute to a total orbital magnetization for the electronic system. So the second contribution to the orbital magnetization is from the edge. So for a finite size system, you always have a boundary. So at the boundary, the electron can feel a boundary potential. This boundary potential confines the electron in the finite size system. So with this boundary potential, the electron actually feel an electric field. This electric field will exert a force on the electron perpendicular to the boundary. So in the presence of finite barrier curvature, together with the electric field, there will be a current along the edge. So this electronic current along the boundary will contribute to a finite orbital magnetization, which is expressed in this way. It depends on the barrier curvature and depends on the total potential, which is the chemical potential minus the electron band energy. So with the modern theory of orbital magnetization, people studied the orbital magnetization of the Haldane model. Yeah, so now you see this orbital magnetization is now zero, even though the magnetic flux of the system is zero. So in this figure, the authors plot the orbital magnetization as a function of phi. This phi is the magnetic flux attached to each area. So when phi is smaller, the band gap is small, and when there is a sublattice potential, when a finite sublattice potential, the flux contributed band gap can be smaller than the sublattice potential band gap. So it's topologically trivial with true number 0. And with larger magnetic flux, the band gap from this magnetic flux is larger. So it's a true insulator. In the true insulator phase, the orbital magnetization is finite, and it can change sign because of the parameter, but there is a outer plane orbital magnetization here. So in this system, the topological property of the electron system is a true insulator, and it have nothing to do with spin here. So we call this kind of true insulator an orbital true insulator. So the next question is how to realize this magnetic flux in the Haldane model. So in the previous realization, it's in a cold atom system, but for a electronic system, it's still a question how to realize it. So in this work, we demonstrate that by employing the Coulomb repulsion interaction between electrons, you can realize this magnetic flux spontaneously. We're considering a Kagomi lattice, so which is a spinless case. So for Kagomi lattice, in the absence of interaction, the bands looks like this. It have a flat band here, and this flat band has a band touching with the higher energy bands. So without interaction, the system is a semi-metal. However, with the interaction V1 and V2, which is a Coulomb repulsion between nearest neighbor and next nearest neighbor, we find this interaction can induce a spontaneous band gap here and drive the formation of a loop current here. So in each triangle, there is a net magnetic flux. So you see the color shows the size of the magnetic flux. So in each triangle, it have a clockwise loop current. And for each hexagon, the flux is have an opposite chirality. So therefore, the system have the net magnetic flux for this whole system is 0. But this loop current breaks the time reversal symmetry, and it can induce a finite orbital magnetization. In this figure, we plot this orbital magnetization as function of chemical potential. So you see inside of the band gap shown by the green region, the orbital magnetization is non-zero. And this system is also a chain insulet. We characterize the chain insulet phase by thread a magnetic flux in the finite size system. By changing the flux by 2 pi, there is a single charge pumping from left side to right side. So this means the true number of system is 1. In this figure, we show the phase diagram of the Honeycomb lattice, of the Kagomi lattice as function of V1 and V2. So V1 is the nearest neighbor repulsion, and V2 is the nearest neighbor repulsion. So we see when V1 and V2 are small, there is a train insulator phase. And when they are large, the system becomes a charge density wave phase with trivial topological phase, with trivial true number. So in this figure, the color means the band gap of the system. So you can see the band gap have a strong dependence on V2, which is the next nearest neighbor repulsion, and a weak dependence on V1. So yeah. So by comparing our results with the previous one, we can see that comparing with the mean field calculation, the mean field calculation says the V1 is enough to realize the train insulet, the spontaneous train insulet driven by interaction. And the V2 is irrelevant. So our DMRG calculation suggests that the V1 is not enough actually, and the V2 is actually very important. So our results also agree with the previous work, which says V1 only can only give rise to a metallic phase. And yeah, comparing with another theoretical work that studied the phase diagram with V1, V2, and V3. So in their phase diagram, the V3 is very important. They need a comparable V1, V2, V3 to realize this train insulator phase. But this parameter region is difficult to be realized. And this phase region is easier for experiments. So yeah, so now up to now we realize that in a semi-metallic system with a Fermi point, the interaction can driven an orbital train insulet. This train insulet have orbital magnetization, but there's nothing to do with spin. So this model can be realized. There are some material candidates to realize the model discussed above. First is this transition metal compound, and second is the metal and organic compounds. So, for example, in this compound, the copper atom form a Kagomi lattice. However, in these systems, in realistic material system, there will always be the electron is not spinless. There will always be spin degree of freedom. So we also studied this Kagomi lattice with spin, and we we're considering, apart from this Coulomb repulsion, we're also considering the exchange between the nearest neighbor electron. So in this work, we find that this nearest neighbor exchange, although it's anti-ferromagnetic, since its J is positive, this anti-ferromagnetic exchange will also lead to a ferromagnetic ground state when J is small. So in this ferromagnetic ground state, the spin degeneracy of this flat band will be lifted. So the model will go back to the spinless one. And we find in this ferromagnetic phase, this Coulomb repulsion will again open the band gap and form a train-insulator phase. So, yeah, up to now, we can compare the orbital train-insulator with the spin train-insulator. So for quantum Hall effect, we have out-of-plane B field. For train-insulator, the most famous recipe to realize it is to use the out-of-plane spin magnetization as together with spin orbital coupling. So in our proposal, we say that actually you can also use out-of-plane orbital magnetization. There, you don't need a spin order to realize the orbital train insulator. So the orbital train insulator has also been realized recently in twisted bilateral graphene system, where the train insulator have finite orbital magnetization, and it is independent of the spin polarization. This is a character of the train insulator, of the orbital train insulator, comparing with the spin one. So yeah, in the following, we are going to ask another question: is can the train insulator be induced by in-plane spin magnetization? So it's basically to ask, is it possible to use in-plane spin to induce an out-of-plane orbital magnetization? So let's first see the symmetry of the take a symmetry analysis. So if you want an train insulator, you will have a y direction current, and when there is a in-plane x direction electric field, that's considering an in-plane spin along y direction. So this, if the electronic system have a mirror reflection symmetry by changing y to minus y, then the whole system will have this mirror reflection symmetry, even in the presence of the spin polarization, because this spin does not change along, because the spin along y direction does not change under this mirror reflection operation. However, this current J is odd, and under this reflection, so and the spin and the electric field are even. So the right-hand side is even, and left-hand side is odd. That means the train number as a function of spin y have to be 0. So this means the mirror symmetry of the system have to be broken. This was reported in this work. And in our work, we realized that apart from this mirror reflection symmetry, there is another two effective time reversal symmetry also needs to be broken. First is the time reversal together with the mirror Z reflection symmetry, because because the spin will flip under time reversal, and it will also flip under the mirror Z reflection. So the spin Y is even under the combined symmetry. and the electric field is also even, and however, the current is odd. So this means if there's this, if the system have this symmetry, the current, the whole current must be 0. So another one is the time reversal with mirror reflection and inversion symmetry. So similarly, so under this operation, the S is even. However, the electric field, it should be EX, is odd because of the inversion operation. So the right-hand side is odd, but the left-hand side, this J is even. So this two symmetries must be broken. This can be realized when you consider a buckled lattice. For example, you can consider a honeycomb lattice with a little bit of buckling, like the silicon. So this buckled structure will break the mirror Z reflection symmetry. Therefore, in the absence of in-plane Zeeman field, both the time reversal and MZ and the time reversal with MZ with inversion are broken. And with in-plane Zeeman field, since the Zeeman field is even under both operations, so the system also breaks the both symmetries. So when the Zeeman field is not along the high symmetric lines, the system breaks all the mirror symmetry and these two symmetry. So yeah, by using this tight binding model, we studied the phase diagram of the system. So this lambda indicates this exchange field strength. So in the absence of exchange field, the system is a Z2 topological insulator with a band gap. When the in-plane Zeeman field is smaller than the hopping T, there will be a band gap open around K and K prime. However, the train number is 0. And when the exchange field is larger than the hopping energy T, the system becomes a train insulator. So this shows the phase diagram. The X and the Y axis represents the in-plane spin direction and its exchange field strength. So when the exchange field strength is much larger, it's large enough, the system will be a train insulator. And there are 6 phases in the phase diagram with alternative train insulator. Along these white lines, the system is metallic, and along this, when they spin along these directions, the system actually have a mirror symmetry. So there cannot be Hall conductivity. So we studied the orbital magnetization along the white line. So you see, the sign of the orbital magnetization is closely related to the train number. So actually, we have this relation, this train number equals to the sign of the orbital magnetization, is minus sign. So there are some material candidates to realize the quantum Hall effect with in-plane Zeeman field. For example, the bismuth bilayer in our work, and also some 2-dimensional atomic layers proposed by based on DFT calculations. So you see the Baire curvature distribution of these train insulators have a negative region here and a positive region here. So it has a finite quadrupole for these systems. So if anyone interested in the third harmonic response, which is related to the quadrupole of the Baire curvature, you can maybe focus on this, take a look at this kind of materials. So now we have the 3 recipes to realize train insulator. First is to use out-of-plane spin together with spin-orbital coupling, which is the most famous recipe. And there's another two recipes related to the out-of-plane orbital magnetization, which is driven by interaction or in-plane spin with spin-orbital coupling. So now we'll turn to the third part, which is about some symmetry protected topological phases. So in the previous talk, we tried to break the mirror symmetry, the time reversal symmetry, and the related symmetries. To break all these symmetries, you can find a true insulator phase. But for the topological insulator, you need to reserve some symmetry, like the time reversal symmetry. By combining two Haldane model with spin up and spin down phases, you can retrieve the time reversal symmetry by make the spin down part a time reversal counterpart of the spin up one. So this for this system with time reversal invariance, there is also gapless edge states here. Since for each copy, it is a translate, so it will have a gapless edge state. Yeah. So these gapless edge states are symmetry protected. The symmetry protection can be argumented in this way. So because of the system have a spin degree of freedom, it has you can define Kramers pairs on the edges. For example, there's a state phi prime. It is a Kramers pair of another state phi related by the time reversal operation. So you can also operate the T on the phi prime. So you can get the original set phi, but you have an additional phase minus sign. So because for a spinful system, the square of the time reversal operator is equals to -1. So if there is a time reversal invariant perturbation, you can see the matrix element between phi prime and phi equals to its minus. So this matrix element have to be 0. It means if the perturbation respect the time reversal symmetry, the elastic backscattering between these two Kramers pair states cannot happen. So the edge state will contribute to a quantized conductance. So this is basically the meaning of the symmetry protection. So we are going to ask what happens if the perturbation breaks the time reversal symmetry. For example, you can use an in-plane Zeeman field to break the time reversal symmetry. So what happens at the edge? So since the perturbation breaks the time reversal symmetry, we expect that the two Kramers states have a non-zero matrix element. So there's a band gap. Our study shows that for the zigzag edge, there's indeed a band gap. However, for an armchair one, it's still gapless. So next we find that the gapless edge state along this armchair boundary is protected by the mirror reflection symmetry. So we can call it a topological crystalline insulator because the edge states are protected by crystalline symmetry, not the time reversal symmetry. So this crystalline symmetry is actually the mirror symmetry. The mirror for a spinful system, the mirror symmetry operator also have a square equals to -1. So by applying a Zeeman field along y direction, the system is mirror-symmetric along y. So at this in the momentum space, we realize that this high symmetric line from gamma to k prime, and gamma point is mirror reflection invariant, since this is the gamma point. By a mirror reflection, this point changes here, but this high symmetric line along gamma does not change. So the mirror symmetry is good symmetry along this line. We can separate the 4 bands with opposite mirror eigenvalues to this red bands have a mirror eigenvalue positive I, and the blue bands have a mirror eigenvalue minus I. So we can study the winding number for each subspace. So you see, for the red band, the winding number is positive, and for the blue band, the winding number is negative. So they have opposite winding numbers, which is non-zero. This non-zero winding number means it's an analogy of a one-dimensional SSH model. So this means in a finite size system, for example, you can consider a cylinder with periodic boundary along y direction. So ky is still a good quantum number. So at the ky equals to 0, this quasi one-dimensional, this effective one-dimensional SSH model will give rise to 2 zero-energy edge states here. So when the momentum k deviates from 0, this zero-energy edge states will evolve continuously, and finally, at this Brilliant zone boundary, this zero-energy edge states will go to the conduction and valence band, form a topologically protected edge states. However, the topological protection is very weak because it needs the mirror reflection symmetry. So if there are some disorders along the edge, there will be coupling between these 2 gapless bands, and there will be a band gap here. So another thing is along the zigzag boundary, we find the system, the gapless edge states shown in gray will become gapped as shown in blue. So, however, this gap along this boundary and this boundary have an opposite sign. So it means there will be a kink state along at the interface between these 2 edges, similar to the one-dimensional SSH model. So this effective model was proposed in our recent work, and yeah. So at the boundaries, there are 2 edge states, which is plotted here. If only one of them is occupied, the charge will be distributed at the 2 boundaries. Each corner have a half quantized charge. So similar results can be obtained in the BHZ model, which is another famous model for the Z2 topological insulator. So here's the summary. For a quantum Hall effect, we need an out-of-plane B field to realize the quantized Hall resistance. However, for a 3-dimensional quantum Hall effect, an out-of-plane B field is not enough. An interaction is required to drive a band gap. And for the train insulator, which is a quantum Hall effect without a B field, there are 2 recipes First is to use out-of-plane spin together with spin decoupling. The other one is to use out-of-plane orbital magnetization, which can be induced by interaction or in-plane spin. And by combining two copies of train insulators, you will find the topological insulator, and which is protected by the time reversal symmetry. By break the time reversal symmetry with an in-plane Zeeman field, we find the system is a topological crystalline insulator. Meanwhile, it's also a higher order topological insulator due to the presence of corner states. So thank you. Is there any questions? Yeah, further discussions are welcome. By the way, I almost forgot to acknowledge my collaborators. The first work, this is my supervisor, Professor Zhenhua Qiao, my PhD supervisor. And the experiment work was collaborated with the experimentalist, Professor Li Yuan Zhang. And the orbital train insulator was done with Dongnan Sheng. And the higher order topological insulator was also collaborated with Professor Niu and Zhenhua. So yeah, thank you. Questions are welcome.
All right, thank you very much, Yafei. That was an excellent talk. At this point, we'll open this up for questions. If you want to raise your hand, you can, or simply shout out, because it'll be hard for me to go through the whole list and find the raised hands.
I've got a question.
Okay.
What is the quantization? So for 2D quantum Hall effect, it's quantized at E square over H. For the 3D quantum Hall effect, what is what is the unit for the quantization?
Okay. So the unit of quantization is basically the electron, the two-dimensional quantization conductance together with a lattice vector, effective lattice vector driven by this Fermi surface instability.
And I have another question. You mentioned several material candidates for realizing the orbital churn insulator. So if I understand, this is a new prediction. Is that correct? Are there experimental groups that are looking to currently realize this type of orbital churn insulator state?
Up to now, I don't think so. There is no realization of orbital churn insulator. The only one is realized is this Maurice, in the Maurice system. There is orbital churn insulator. But for the finite, for the usually the two-dimensional crystal, there is no reported on the orbital churn insulator.
And for the twist bilayer, the slide that you just showed, can you comment on the mechanism that gives rise to orbital churn insulator?
Okay, so in this twist bilayer graphene system, usually you will have flat bands at each valley. So for K valley, you have a flat band. For K prime valley, you have a flat band. And by breaking the inversion symmetry of the system, for example, by using a boron nitride substrate aligned with one of the graphene layer, you can realize so from the single particle band, you can realize a churn insulator in K valley and K prime valley with opposite churn numbers. So it's similar to a quantum spin Hall effect, but the system is have a flat band. So in the presence of interaction, the interaction can drive a valley polarization. So the electron can only fill one valley. So in the one valley, the system will exhibit a finite churn number.
Okay. And the orbital magnetization comes from dominantly one valley?
Yeah. From the one valley. Since you know the gapped graphene, so in gapped graphene, the K and K prime valley electron have opposite orbital magnetization.
Okay, thanks.
Well, if I have other questions, I would like to ask, or maybe make a comment. I can't claim to understand all of the topological aspects of this, but the idea of looking at the presence or absence of open orbits and looking at that through the longitudinal and transverse magnetoresistance, that's a very old idea. In fact, I wrote my PhD thesis in 1961 on the galvanomagnetic effects in cadmium and zinc, where the main point was to look at the asymptotic behavior at high field, and it tells you whether you have open orbits or closed orbits, and that depends on the direction of the magnetic field. In some directions you have open orbits, in some directions you have closed orbits. So
Okay.
very similar ideas.
Okay. Thank you.
So can I ask a question?
Yeah, sure.
Go right ahead.
So in the mirror symmetric protected edge states, so as far as I can see, you have something similar to graphene, but with an AB asymmetry. And that's what generates the gap. And now, but okay, so is there any other component that we need? Because, for example, molybdenum disulfide looks very similar to this.
Sorry, let me see. So you mean the band gap here?
Yeah, meaning like the AB asymmetry in the honeycomb, right? So it leads to the gap at the K and the K prime, right?
Yeah, but here in this work, the band gap is not induced by the sublattice potential. It's induced by it's basically the Kim-Mali model. It's induced by the intrinsic spin-orbit coupling. Here.
Okay, so in addition to, so you need an intrinsic spin-orbit coupling. So can we say that for this MY, let's call them MY protected edge states, you need a spin orbit and inversion symmetry too, like the MY protection too?
Yes. So
both.
So for this system, the bulk band gap is induced by the intrinsic spin-orbit coupling, and when there is an implant Zeeman field along y direction, so the spin-up and spin-down band split, and this Zeeman field respects the mirror reflection MY.
Okay, so it's so basically I can we artificially make it by in-plane magnetic fields?
Yeah, you can.
Okay.
Yeah, and for this system, the implant Zeeman field do not have a orbital effect, right? So it's a purely a Zeeman effect. There will be no quantum Hall physics.
So the necessity that the MY operator squares to 1, it squares to, you said that the square -1, right?
-1, right.
It's for this, it's to have like it's to mimic time reversal, right?
Yes.
So basically you broke time reversal by the Zeeman field, but you substituted the symmetry by MY, which behaves like a time reversal operator.
Yes. It's similar. It's similar to time reversal. Yeah.
It's similar to time reversal.
Yeah, but it's weaker than the time reversal.
So do we have kind of Kramer pairs or the analog of a Kramer pair?
Yeah, you can define the Kramer's pair along the edge with mirror reflection symmetry. So for example, these two states are reflected by the mirror MY.
Okay.
And so that can be regarded as a Cramer's pair.
Cramer's pair of mirror symmetry.
Of mirror, yes.
Of mirror symmetry. Oh, that's
Yes.
good. Okay, thank you.
All right, any other questions?
May I ask for the first topic, the 3D quantum Hall effect?
Yeah, sure.
You discussed experiments in a particular system.
Yeah.
Now, what kind of system are you actually, or what kind of material are you actually looking for realization? What would be like the main criteria to choose materials if you were interested to look for this effect in other materials?
Yeah, so this is a good question. So I think the first requirement is that the mobility of the system have to be very high. So you have to have a very clean system. And the second is that it's better to be a direct material, because for a direct material, with a small Fermi surface, the electron density will be small, right? Because the density of states for a linear dispersed bands is smaller than the density of states of a quadratic bands. So this means the electron density of states is small, and you need a smaller B field to realize the quantum limit. So if the density of states is very high, you will require a very high magnetic field, which can be difficult to be realized. Yeah, so the other one is you better have a strong coupling between electron and lattice. So, for example, for soft materials, you usually have a stronger electron-phonon coupling. So in that case, it might be easier to realize the interaction-driven instability. So, yeah, I think that is basically 3 criteria.
Right. So do I understand correctly that kind of in contrast to an ordinary 2D quantum Hall effect, disorder for this mechanism would be detrimental? That's why you need a high mobility. Is that kind of the argument?
The high mobility is required also in 2D systems. So you see, people have studied the 2-dimensional electron gate for a long time, and but the 2D quantum Hall effect was discovered by von Gliesen. In his sample is very clean comparing to the previous ones. Therefore, it's very important to have a clean system. Otherwise the broadening of the lambda level, if the broadening of lambda level overcomes this cyclotron frequency, think it's hard to realize quantized resistance.
But, okay, so may I ask, so in my naive understanding of this phenomenon, I would say that if you have a 2D system with a high degree of disorder, the states, the broadened states, except for the state in the middle, that would be localized in the bulk, and therefore the quantum Hall effect would be realized. So
yeah, the disorder effect is important, but the disorder cannot be too strong.
Okay. All right. And yeah, maybe just out of curiosity, you were mentioning this the third harmonic response. So what is this actually about? Or what would one measure? What does it actually mean to measure third harmonic response? That's for it, for the second topic. You mentioned that there is a proposal there.
You mean the orbital translator?
Yeah. Sorry, I was jumping to the other
Okay.
topic.
So for the orbital translator, for example, we can take this TJV model. This one. Yeah. For usually for a spin-induced translator, the Hall conductance is combined, it's bounded to the sign of the spin polarization. So if you have a spin up, you have true number 1. If you have spin down, you have true number -1.
Okay.
But for this orbital translator, the true number is not depend on the spin direction.
Mm-hmm.
So for example, in this phase 1, it's basically you have a loop current along the system in the whole sample, but the spin, the ground state have a spin degeneracy. So when the spin rotates in the Bloch sphere, it's as a ferromagnetic ground state, the true number does not change as long as this loop current does not change sign.
Okay.
So yeah, that is the key difference between the orbital translator and spin-induced translator.
Okay. Yeah, I'm not quite sure. So you were saying, like, you know, when you before finishing the subject, you said that, you know, one way to measure would be to look for the third harmonic response. I'm just not quite sure I understand what this actually would be. What would one measure?
Okay, I think you can measure the Hall conductance by change as a function of the spin direction.
Mm-hmm.
So if for example you have a spin along one direction and opposite direction, if they have the same, if the Hall conductance have the same sign,
Mm-hmm.
then you have an orbital translator.
Okay. So that's what you call. I see. Okay. All right. Yeah. Thank you.
Thank you.
So this is a asymmetry in the Hall conductance.
It's
as you measure one direction versus the other.
Yeah, it's a symmetry property, I think. So if the Hall conductance does not depend on spin, it's an orbital translator. If it depends on spin, it's usually a spin-induced translator.
Can I ask about the topological classification of the mirror-symmetric topological insulator?
Mm-hmm.
Because what as far as I understood is that you measure the Berry curvature of one band and the Berry curvature of the second band, and you subtract them. Mm-hmm. But the result is an integer of the difference between them.
Okay, so if the spin is a good quantum number, then you subtract them, you get an integer number.
The difference is always an integer if the spin is a good quantum number.
Yeah, because for each spin it's an integer, so their difference must be an integer.
So it's always an integer. But then the problem is that, okay, so if I understood right, is that you need to have a Zeeman field, right, in this type of system?
Yeah.
So that,
So first you need a Z2 topological insulator, and then you need a Zeeman field along one, line implant.
And so basically this is, it becomes a Chern insulator, the full system at the end.
No, it's not a Chern insulator. Because there is a mirror symmetry, MY. In the presence of mirror symmetry, the system cannot have Hall conductance. Okay, because the mirror symmetry prohibits the presence of Hall conductance. So finally, the system is you can call it a topological crystalline thread, or you can call it a high order topological thread, but it's not a train thread.
Okay.
So it's different from, so here we studied a planar honeycomb lattice in the third part. So in this part, we study a buckled honeycomb lattice. This buckling breaks the neurosymmetry. So that is the key difference. In the presence of buckling, you can realize a train thread. But without the buckling, you cannot.
Yeah, but the number at the end of the day, the number that identified the topology of the system, right?
Yeah.
Was simply the subtraction of two Chern numbers.
No, it's a, okay, so you mean here?
Yeah.
Okay, here it's not a Chern number, it's a winding number. This winding number is a one-dimensional, it's defined in one-dimensional system. So, so you see there is a mirror symmetry MY. So you need to find a line that is mirror symmetric in the Brilliant zone. So this line is from this gamma to this gamma point. However, when you deviate from this high symmetric line, for example, this for example, you study a K point here, and the mirror reflection it becomes this point. So it's not a mirror reflection environment. So along this high symmetric line, it have a mirror symmetry. So you can separate the 4 bands into 2 subspaces. Each is a 1D system, effective 1D system. So this 1D system have a winding number. Okay, so it's different from Chern number. So it's basically the one-dimensional SSH model.
So I guess we're going to we'll keep this conversation going, but you're beginning to lose the experimentalist here over time. So I'm going to stop the recording here and just remind everybody we will pick up with this again in spring. If anyone has any recommendations, the science board or I will take any recommendations you have for speakers. Just send them to us. You can find our emails at acme.ua.edu or simply find us online.